So now that we understand conceptually what vertical and horizontal asymptotes are, let's go through a couple examples where we identify vertical and horizontal asymptotes given a graph, and then we'll talk about finding vertical and horizontal asymptotes when we are given a rational function written out. So here we have a graph of the rational function y equals x squared minus 4 divided by x squared plus 4x plus 4. Identify any vertical and horizontal asymptotes. Well, recall, vertical asymptotes occur when our function values, our y values of our graph, approach positive or negative infinity as x approaches some real number. Notice here at x equals negative 2. As my x values approach negative 2 from the left, my y values go up to positive infinity. As my x values approach negative 2 from the right, my y values approach negative infinity. The graph keeps going down and down. We say here that the function increases and decreases without bound as x approaches negative 2, and therefore we have a vertical asymptote at x equals negative 2. To determine our horizontal asymptotes, we need to look at the end behavior of our graph. What do our y values do as x goes to positive infinity, and what do our y values do as x goes to negative infinity? Here on our graph, as our x values go to the right, we notice that the y values are getting closer and closer and closer to 1. Similarly, as the graph goes to the left, as the x values go to negative infinity, the y values get closer and closer and closer to 1 as well. Because our graphs approach 1, as the function goes to the left and to the right, we can say that we have a horizontal asymptote at y equals 1. All right, a couple things to make note of here. Asymptotes are always written as equations of lines. They are not numbers. So this is the vertical line, x equals negative 2, and this is the horizontal line, y equals positive 1. Make sure you are labeling your vertical and horizontal asymptotes appropriately as equations of lines. If you do not write them as equations of lines, you will not receive full credit. Please pay careful attention to that. All right, let's look at another example. Here we have another rational function, a polynomial divided by a polynomial. This one is y equals 3x divided by x squared plus x minus 2. So, to identify vertical asymptotes, we need to find anywhere where our function increases or decreases without bound as x approaches a real number. Well, again, here at x equals negative 2, notice as the x values approach negative 2 from the left, the y values go down to negative infinity. And as our x values approach negative 2 from the right, the y values approach positive infinity. Because the function increases and decreases without bound as x approaches negative 2, we have a vertical asymptote at x equals negative 2. Similarly, here at x equals 1, as my x values approach 1 from the left, the y values go down to negative infinity. As my x values approach 1 from the right, the y values go up to positive infinity. Because the function increases and decreases without bound as x approaches 1, we have a vertical asymptote at x equals 1. Again, notice that these are written as equations of vertical lines. Now, to find our horizontal asymptote, we need to look at the end behavior of the graph. Well, as my x values go to positive infinity, as the graph goes to the right, the y values of the graph get closer and closer and closer to 0. Similarly, as the x values go to negative infinity, the y values of the graph get closer and closer and closer to 0 as well. Therefore, we can conclude that in this case, we have a horizontal asymptote at y equals 0. One thing to make note of, it is possible to have multiple vertical asymptotes. When we are dealing with rational functions, that's a polynomial divided by a polynomial, if there is a horizontal asymptote, you will only have one horizontal asymptote. So let's take a look now at finding vertical and horizontal asymptotes when we are given the function. Let f be a rational function given by f of x is equal to n of x divided by d of x. Again, rational function is a polynomial divided by another polynomial. All right. This is important, where n of x and d of x have no common factors. If this is the case, the graph of f has vertical asymptotes at the zeros of d of x. In other words, we are looking for the zeros of the denominator. Given that we have no common factors, what makes the function undefined? That will give me my vertical asymptotes. The graph of f has one or no horizontal asymptote, determined by comparing the degree of the numerator and the degree of the denominator. N of x is the numerator, d of x is our denominator. There are going to be three different scenarios to look out for. Scenario number one, if the degree of the numerator is less than the degree of the denominator, the graph has a horizontal asymptote at y equals 0. Scenario number two, if the degree of the numerator is equal to the degree of the denominator, the graph has a horizontal asymptote at y equals a sub n divided by b sub n. This is the ratio of the leading coefficients. Notice a sub n up here. That's the leading coefficient of the numerator. B sub m, that is the leading coefficient of the denominator. So we're going to take the ratio of those two to get our horizontal asymptote if the degree of the numerator is equal to the degree of the denominator. And our final scenario here, if the degree of the numerator is greater than the degree of the denominator, the graph has no horizontal asymptote. So those are our three cases. Let's put this information to work. So find the domain and identify any vertical asymptotes of f of x. Here we have f of x is equal to x squared minus 9 divided by x squared minus 2x minus 3. Now, when you guys are dealing with these rational functions, it's always going to be helpful to begin by writing the numerator and denominator in factored form. In this case, our numerator factors into x plus 3, x minus 3, and our denominator factors into x plus 1 times x minus 3. This allows us to easily find our domain because, as we know by now, the denominator of a fraction can never equal 0. When does the denominator equal 0? Well, the denominator equals 0 if x is negative 1 or if x is 3. Therefore, we can conclude that our domain is all real numbers except for x is equal to negative 1 and x is equal to 3. Now, wherever your function is undefined, one of two things is going to happen. You will either have a hole in the graph or you will have a vertical asymptote. All right, I'll say that one more time. Wherever your function is undefined, you will either have a hole in the graph or a vertical asymptote. So let's think about finding vertical asymptotes. As we said on the last slide, when identifying vertical asymptotes, cancel common factors between the numerator and the denominator. We want to get rid of any common factors. Well, we notice that x minus 3 and x minus 3, those are common factors, and so we can cancel them out. Those divide out, leaving us with x plus 3 divided by x plus 1. All right, given that we have no common factors, the remaining zeros of the denominator give us vertical asymptotes. So what's our remaining zero of the denominator? X equals negative 1, and therefore we have a vertical asymptote, VA, at x equals negative 1. All right, now let's talk about horizontal asymptotes. To find horizontal asymptotes, we need to analyze the degree of the numerator and the degree of the denominator. Now, you can do this once the common factors are canceled out, but I find it's easiest just to look at the original rational function where we have a polynomial over a polynomial. And in this case, the degree of the numerator is 2, and the degree of the denominator is also 2. If the degree of the numerator is equal to the degree of the denominator, then we have a horizontal asymptote at the ratio of the leading coefficients. Well, the leading coefficient of the numerator here is 1. The leading coefficient of the denominator here is also 1. 1 divided by 1 gives me a horizontal asymptote at y equals 1. All right, and if you were to plug this into your calculators, this is the graph that you would get. Notice we have the vertical asymptote at x equals negative 1, And we also have a horizontal asymptote at y equals 1, right? As my x values approach -1, the function, the y values increase and decrease without bound. And as my graph goes to the right, as x goes to infinity, the y values approach 1. As x goes to -infinity, the y values also approach 1. So, the next question is, what happens when x is equal to 3? As we said already, the domain is all real numbers except for -1 and 3. And we've recognized that we have a vertical asymptote at x equals -1 because we were able to cancel out this common factor of x minus 3 and x minus 3, and -1 was the remaining zero of the denominator. So, this is important. Any values of x that are not in the domain and do not correspond to vertical asymptotes will result in holes in the graph. So we were undefined here at -1 and 3. We had a vertical asymptote at x equals -1. That means that x equals 3 must correspond to a hole in the graph. So we have a hole in the graph when x equals 3. It would be right here. We just put an open circle on our curve. Now, to find the coordinates of a hole, what we do is we plug the x value into the simplified version of the function. In other words, the version where we have canceled out those common factors. So if we cancel out our x minus 3 and our x minus 3, and we now plug in 3 into our function, we get 3 plus 3 is 6, divided by 4. 6 over 4 reduces into 3 halves. This means that our hole is located at 3, that's the x-coordinate, comma, 3 halves. And does that make sense based off of our graph? Yes, the x-coordinate is 3, and the y-coordinate is 1.5, or 3 over 2. All right, and so that is how we find the coordinates of any holes. So there we have it, identifying domain, vertical asymptotes, horizontal asymptotes, and the location of holes for our rational functions. In the next few slides, we are going to go over graphing rational functions, which is going to include taking all of this information and using it to help us to sketch a graph.